So it's a pleasure for me today to introduce Professor Janos Sztipanovits from Vanderbilt University. Welcome him back. He was here at the Cyber Physical Systems Week a few years back. So Janos has a long and distinguished career in embedded systems, software modeling, and so on. He's also a founder of the Institute for Software Integrated Systems at Vanderbilt, a big operation, 130 people. In addition to, so to say, a career in academia, he's also been heavily involved in influencing research politics, both in the United States, in the program on cyber physical systems, and also in Europe. We were fortunate to have him here today. He's spending a week in Sweden and toured the 3 universities. He will be here also in the afternoon, so if you happen to not be on his schedule now and would like to have a chat, just let us know. But with that, we are looking very much forward to your talk, so please, Janos.
Thank you very much, Kalle. Thanks for the invitation. I would like to use the time now to talk about both cyber physical systems and model-based design, and show you how these two things are coming together in the context of a particular project what we are engaged in the last 2.5 years now. The project is a quite big one. Our side of the project is primarily the design automation tool suite. There are a number of people working on the project at ISIS. Here is the list of the lead researchers. We have altogether about 35-40 people working on this. So certainly what I'm talking about is the work of many people. So I need to give credit to all of the wonderful folks who are doing this. What I will do now is that I give you first an overview of a kind of large-scale experiment on cyber physical systems and model-based design. That experiment is funded by DARPA, specifically the DARPA's Adaptive Vehicle Make program. It started up in 2010, and right now we are about in the middle of the program. I will first describe the program, and then we'll pick a few of the challenges that are interesting, particularly from my point of view, but hopefully for you too. There are many other challenges, but I will not touch on, but perhaps mention it. So first I will talk about the so-called cross-domain modeling challenge, then go over to a concept what we use extensively in this project, model integration languages. I will describe the so-called open meta integration framework, which is the design automation substrate what we are building. Then I will go through on some aspect of the overall problem that quite a bit influence on how we approach this, and particularly the need for formal semantics and what we do in this area. So that's roughly my plan. Usually I can go through on this barely, but I will adjust the speed as your interest requires, and as I'm getting lost in one or the other areas. So let me talk first about this program. It's more than a decade ago. There was a program at DARPA called Model-Based Integration of Embedded Systems. That was actually my program. Back then I was at DARPA at that time. That program, the Adaptive Vehicle Make program, is ultimately looks into model-based design after a decade of MOBIs. See where did we get after 10 years, see what's the reason for limited penetration of the technologies, particularly in the defense industry, and see that through a very specific challenge, which is defined in this program. EVM is targeting to create an end-to-end model and component-based design and integrated manufacturing view on the process. The specific target is to create an amphibious infantry vehicle that will become a specific vehicle which was coming out of the foundry, which is built also in this program. So it will be not only an infrastructure building program, but immediately an evaluation program, which is targeting a quite complex real-life cyber-physical system. Altogether, the program lifespan is 5 years. It may go a bit over because scheduling issues. So I would tell that it's about 5-6 years what it will take. In this program, it's always, of course, an issue whether the program survives the continuous milestones and related evaluation. So far, we are doing reasonably good. I will talk about later what does it mean. Now, DARPA set an engineering and economic goal suite that centers around 3 major points. One is that after analyzing the related industries, so it's obviously DARPA's main concern is defense industry, but if you look VLSI industry, automotive industry, and others, it was not unreasonable to demand that there has to be somewhere enough space in the technology that by inserting extensively model-based design, the current development time can be decreased by 80%. It's obviously if this is coming through, it's some fantastic gain. How much it will be materialized, it will be measured very carefully, and actually it is measured right now. The second main goal was that it's very common in the defense industry that companies are developing systems such that they are developing it for their own manufacturing base. Now that means that the dependencies between the manufacturing capabilities and technologies and the design is not explicitly expressed and modeled. So ultimately, that creates the situation that after finishing the design and the system goes into manufacturing, it's almost impossible to port the system production into another manufacturing base because they are so intertwined. The VLSI industry was changed fundamentally by separating design houses and fabrication. Right? That came by 20 years ago almost. So DARPA's other agenda is to somehow recreate the similar situation in cyber-physical system and build a strong interface between design and manufacturing so that the interdependencies are made explicit, modeled, and open up the opportunity to create fabless design houses for CPS and separate programmable foundries. So that's the other major goal. The third goal is the so-called democratizing design goal. The best to relate it to a fact. 20 years ago or 23 years ago or so in the early 90s, one C++ compiler cost about $10,000, occasionally $30,000. Then the Visual Studio came by and it pushed down the price overnight to $300 or $200. The consequence of this was pretty dramatic. It's basically opened up the whole software development field for the small developers, small software houses. Right now, the engineering tools that has to be used in CPS design are extremely expensive. It's not rare to have $50,000, $60,000 per seat tools or more. So that's the third intention, how to create a tool base which is open source, easily accessible, not necessarily in a shrink-wrapped form, but presumably a software for service model, and push down really the price and opening up the field for cyber-physical system design through this. Now, let's go to the scientific challenge part. From the science point of view, really the main issue to achieve the AVM's goal is that you push out the limits of this so-called correct by design or correct by construction method. Now, in this context, correct by construction would mean that you progress during the design such that your primary artifacts are models, models that are well understood, well analyzed, and the models and the methods that are used for building them, analyzing them, verifying the artifacts, and making the simulations are good enough that you can make, at the end of the design process, strong, predictable design. So you know what will come out from the manufacturing lines with a good enough fidelity. Now, there are several issues that push against you to approach this goal. One is that in cyber-physical area, the separation of concern principle is very widely used. Simple, the design of these systems that have many physical and computational aspects, cost aspects, manufacturing aspects, is decomposed into different fragments. They are usually isolated, and the separation of concern basically means that you focus one or other design objectives. And at the end, you will see in the system integration lab whether this separation of concern was acceptable, or they are unmodeled interactions across that finally result in a manufactured system which doesn't meet the specification. So that's the bottom line. So accordingly, one main issue what we followed in building up the design infrastructure is that we pursue multi-physics, multi-abstraction, and integrated cyber-physical system design flows. Much of the effort goes into modeling cross-domain interactions in the flows. Obviously, that increases the modeling complexity. But a counterpart to this is that we are pursuing very heavily component-based design. So my hope is that even if the overall model complexity is increasing, if we use reusable component and automated composition techniques, then still productivity can be kept up. The other part which is interesting from scientific point of view, that when you do multi-modeling and you want to use together these many different kind of physical and computational style models, then the integration of these models such that you can express the cross-domain interaction is absolutely mandatory. Model integration and cross-domain modeling is a fascinating problem. It's ultimately the condition for design automation, and the solution is non-trivial. So the method, which is the name of the design automation component or the design tool component of the program, uses extensively model integration techniques, and we push quite heavily a so-called model integration language, sci-fi, that I will talk about later. Now, the project is divided up into major technical areas, so let me just put together the whole picture for you, that how the project is running right now. one core element of the program is the so-called Open Meta Tool Suite. The primary deliverable for this component is an open source design tool suite, which integrates really a large set of tools, composition methods, and many others that are used in the overall design process. As much as possible, we stick with using open source tools. Many of these tools are coming from Europe. Other tools are coming from the US. Many of them what we develop, but ultimately what's emerging here is really an integrated tool suite. The tool suite is linked to another component called Vehicle Forge. You all know what is SourceForge and what are the SourceForges. These are basically software repositories that enable crowd-sourced development and widely used. Here, DARPA's ideas was that why don't we recreate it for model-based design, and the Vehicle Forge suggests that it's basically some kind of variance of the SourceForges, and it will include a crowdsourced model repository, a certified, curated model repository for components from which vehicle and related cyber models can be built. But in addition, the Vehicle Forge provides also a lot of other services, not only as a repository for the models, but it provides the user management infrastructure and also the entry point to the overall analysis infrastructure. So that's why this link here, which suggests that Vehicle Forge communicates with the Meta Tool Suite such that components, designs, and design spaces pass toward that, analyzed, and the analysis results are sent back to the Vehicle Forge environment and interacts with the users. I will talk more about this. The third major component in the project is the development of a model library, a primary model library for the components, and curation of these model libraries. Curation means that I will show you what is the AVM component model. These component models have a number of standards that are used to pack together the component model, and curation means that all of these that are getting into the component exchange on Vehicle Forge are thoroughly tested, checked, and blessed after they get into the repository. The fourth element, which is quite critical to the whole concept, is the so-called foundry. The foundry is a fabrication facility which can receive design data from the design tool suites in the form of a standardized design data package and able to run an analysis on it to decide manufacturability, whether it fits the manufacturability constraints, and send feedback to the design tools such that the design can be refined, modified according to early indications of manufacturability constraints. The Foundry is not just a program. The Foundry is a physical system. It's a physical site. It's a real facility which is being constructed now. That facility will integrate the vehicles themselves. And I think that at the end of it, the program will build 2 to 5 vehicles. These are relatively big vehicles. We expect that they will be roughly 20-ton vehicles. So the size and complexity is quite there. Now, finally, there is an interesting aspect of how the program is structured. All of these 4 components I talked about are the fundamental components. Basically, you can tell that these are the infrastructure. The testing is constructed such that a competition has been created. The FANG is the name of the vehicle which will be designed and constructed here. The competition is a prize-based competition, and the prize is structured such that there are 3 phases of the design. the drivetrain design, the hull design, and the full vehicle. The price for the drivetrain is $1 million, for the hull is $1 million, and for the full vehicle is $2 million. In the US, there is quite a culture of these price-based design competitions. It's the way of life, what people accept, that these are winner-takes-all type of competitions. So certainly the stake is there, but the experience is that there is significant interest, even if the rules are tough. So finally, the community is the user community who are the FANG competitors. They are actually using the whole tool chain, build the designs, test the designs, totally in a virtual environment. And the winning designs are selected and sent to the foundry, and the prototypes will be built for the winners. Now, we know that, at least at this point, that structure is working. The first version of the whole tool suite with all of these components, what I showed you, has been completed during the last few months. The competition for the drivetrain started up in January 15 and concluded in April 15. We know that they are already a winning design, which was not announced yet. It's also interesting to note that there were over 1,000 competitors signed up on Vehicle Forge. There was roughly 170 design teams that started up working. The size of the design teams were occasionally one person, but there were quite large design teams, totally distributed in the country. And they used the collaboration platform, but Vehicle Forge provided that. So ultimately, we are going now in the phase when the selected winners are evaluated, and after the winners are announced, two of the drivetrains will be built during the summer and tested against the models. So that's the immediate next step in the program. And parallel with this, we are making another spiral on the tool suites and model libraries and so forth, because I must tell you, we learned a whole lot. What's the difference between principle and practice in this regard. Our group is responsible for the blue area. So we are the primes for the Open Meta tool suite, for the Vehicle Forge, and for the curation of the model libraries. Two other organizations are involved also in the program. The Foundry is designed by Penn State, and the whole competition and the primary model library is created and run by Ricardo, which is, I guess it's a British company. Now, let me close that part to show to you some of the user experience, what the folks who are getting an account on the Vehicle Forge see. So first of all, originally it was planned that it will be a worldwide competition, so it will be open everyone. In the first round, it's an only US competition. So that's a restriction. It's required that who wants to get a user account needs to be US person. So that's the restriction now. So you see when you get into the site, you see the component library. The component library has a tremendous amount of information about the components. There is, of course, an ontology build-up for all of the components, so you can browse it. You can pick components according to different parameter ranges. Then you can inspect the component. You can get access to the component, all sorts of information, different levels of fidelity, dynamics models, CAD models. And there is a set of I will talk about it, what belongs to a component model. So the component repository or component exchange is one key element. We have right now about roughly 1,000 components. What we will end up with the refinement, it will be a low 1 or 2,000 for the drivetrain part. It will continue their components for the rest of the system. What's going on right now is building up the appropriate components and component concept even for the hull and then full vehicle. The other concept through Vehicle Forge is the concept of the design projects. The design projects are created. Members are the designers who form basically a team. They will get access to a suite of self-provisioned collaboration tools, wikis, discussion forums, issue tracking, all sorts of coordination mechanisms, what you can imagine. There are design data repositories on JIT and SVN. There is a quite extensive project access control so that it's kept confidential during the competition. There is an extensive notification and messaging system because obviously in the current schedule, the tools were co-developed, frankly, by the model repository and by the design. So there was a whole lot of need for sending messages around, and also the Jira, which is the message board for issue tracking, was pretty heavily used. So that's the design project aspect of it. So when a team came together, they create basically a design space for them. They can download those tools that are to be stored in their site, but the high compute load tools, complex tools, are deployed in a cloud server. So, for example, the large simulators, we use Daimon right now in this phase until Open Modelica reaches the appropriate level. These are all cloud deployed tools, so the designers really don't have to have that kind of computing horsepower that needed to do the pretty deep analysis for evaluating certain aspects of the designs. And there is a third aspect, which is the whole designer management. There is an extensive profiling support for social networking, team building, and all of these things on the Forge. Now, let me go to another domain and go to the whole cross-domain modeling challenge. What you can certainly see from this aspect that the project itself has really interesting point in several areas. Not only what I will talk about now, but also from the point of view, what does it mean doing collaborative design in this area? How to do collaborative design? And it's certainly an interesting opportunity for our team to have detailed measurements, how the designs were developed, what kind of analysis were done, how the groups used the analysis background. We could see, for example, clearly that the dominant use of the infrastructure was late evenings, midnight, and then it started going down toward the morning. Weekends were also heavily used, so many of the designers were having jobs somewhere, and they came together and run this whole project on the side. So there are many interesting aspects what gradually we will process and report. Now let me go to the whole cross-domain modeling challenge. These are the AVM components from the drivetrain point of view. As you see, nothing unexpected. These are engines, transmissions, couplers, battery, vehicle management hardware, servos. There's many kind of things that are physical or cyber-physical. In this phase, the cyber part only, the software part only, was not heavily in the front because the components usually embedded these elements. But progressing toward the full vehicle design, that's becoming rapidly bigger and bigger weight. Now, when you look at these components and you see that that ultimately what you need to do is to get these, understand them, compose them, and understand what you did, and what will be the key properties of the key subsystem. And finally, you take the whole design and you submit to testing, automated testing, so that you can get a score for it. So a lot of things needs to be solved. So that's a quite interesting problem in itself. This slide shows roughly the component model, how it's built up. That example is actually taking elements from the Caterpillar C9 diesel engine. So the components internally, if you look in the internal anatomy, they have a suite of parameters and properties. The difference is that the properties are immutable, the properties are mutable during the design. So it's very typical that for design space exploration, we want the components to be parametrized. These will be the tricks, one of the tricks at least, what the designers can use to adopt their design and change their design. Obviously, things like for that engine, the number of the cylinder is fixed. But there might be other things that are adjustable. Now, besides the parameters and the properties that are basically static things, there are a bunch of other things that are very important for the overall analysis. One of them is the dynamics group. There are a suite of dynamics models associated with the component. We have different kind of model types that we allow to represent dynamics, lump parameter dynamics. The common thing is that we have now, first of all, we use Modelica. That's the primary modeling language for it. But we structure the whole system such that we can use hybrid bond graphs also and Simulink. The Modelica libraries have high fidelity and low fidelity versions. The high fidelity and low fidelity versions are created such that they all talk about exactly the same component, just let's see the phenomena, the physics phenomena that are looked at is deeper in one than the other, or simplifications are accepted. Obviously, the primary need for using different fidelity is that when you start building up or composing all of these models and get large models for the assemblies and the system, what you need to analyze, simulate, verify, then it's extremely important that you look into that from the point of view of the property, what you want to figure out, where do you need the high fidelity and where do you need only the low fidelity component to manage somehow the complexity. There is a lot of problem with that issue, clearly. So there are lump parameter dynamic models, and finally there are, of course, CAD models. CAD models exist also in a detailed geometry version, primarily for the manufacturability and manufacturing related design steps. And there is a finite element analysis related CAD model set, which are lower fidelity and sufficient for gridding and running different kind of analysis, so temporal properties and others. Now these components, what you see here can be considered then a container for a bunch of models that are all related to that particular component, characterizing that component. You can see the whole model exchange as a glorified catalog. It was an interesting issue that how the different companies relate to providing information for this. We have many different kind of experience with this. Clearly, you can construct dynamic models such that you primarily model the physics. And all of the, let's say, proprietary or conceived proprietary information is linked to the parameters. So that's certainly one tactic. The other is that, you know, if, what we believe, that if the whole thing start catching up, it's the company's best interest to disclose what their component can do, because otherwise they cannot be part of the overall design or design space exploration process, what the whole tool chain is doing. So we shall see how it will work out. Now the components, of course, therefore they need to interact with others. Therefore the AVM component model needs to establish the standard interfaces for this. We have 4 interface types right now in the first release in the components. We will revise it some. One is the parameter and property interfaces. Clearly, when you decide what are the component level parameters and properties, there is internally a mapping between these and many, many parameters that internally the component might have. So these are aggregates. The mapping between those and the detailed, let's say, simulation-related parameters and so forth are also captured. That's an important point. The second set of interfaces is the so-called signal interfaces. The signal interfaces are what they tell us. These are signals. Information is flowing through them. These interfaces are causal, directional. They express logical connection, and they don't assume that power is flowing through these interfaces. These are basically the signal flows that relate to the cyber part of the overall system. The third set of interfaces are the power interfaces. These are for the physical composition. These interfaces are acausal. They relate to physical phenomena. They are strongly typed. It's standardized what are the actual physical variable pairs that relate to different energy transfers, and they ultimately represent power flows in the system. There is a mapping again between the power interface points and internally the dynamics models. That mapping is described power port mapping, and it's part of the models, of course, themselves. Finally, there are the structural interfaces. The structural interfaces capture the geometric constraints that you need to resolve when you stick together components. So these are surfaces, different kind of constraints. What does it mean to link together 2 components? And then if a tool, and of course tools are available for this, when you use these interfaces and stick together the components, the alignment can be computable by generating solutions for all of the geometric constraints. Going further, there is a set of other models that are important, and we are now start going out to another modeling issue, which is not anymore the core component properties, the dynamics, the geometry, and different static parameters and the interrelationships, but the structure of the design. Certainly in this category is the interface model themselves, because the interface models are used for building up architectures, system architectures. So we need to have a way to represent the designs. So you can tell that whatever you see here are now relate to the integration language, what we use on the top of these component modeling languages. You can also imagine, even at this point, that these architecture description languages or interaction description languages and their semantics is much, much simpler than what you need for describing the semantics, let's say, of Modelica, right? Ultimately, you allow to this level add to those kind of semantics that you just need for understanding what happens across the components and not more. Now let's see what happens here. Designs, of course. The designs are instantiated and connected components. They have composed parameters, behaviors, and geometries. The design models can be wrapped also as a component, so for a higher order component or an assembly, another component can be created. Clearly, the lowest level component don't have any internal structure from the point of view of the synthesis tools, but in the design, of course, everything is open. And again, if we take an assembly, we can aggregate the component interfaces, and we can get a higher level single set of system interfaces. A very essential element of the overall approach what we built up in Meta is the concept of design spaces. Design space comes in the picture the following way. When you want to build design, let's say for a drivetrain in that category, you could just imagine that the only thing what you get to start up the whole thing that someone dumps to you 2,000 component models. That would be a pretty hard thing to start building up a design model from scratch, just knowing the components. The real practice is that during an engineering process, primarily which is coming from history, you have good design points. We consider them seed designs. These seed designs are a key concept to elaborate the design spaces. Ultimately, even in the competition, we provided one seed design which represented a reasonable vehicle architecture, and people could start enriching and building a design space around the seed design. That design space building has a set of methods. One is that you use the parametrization, and you define that what are those parameter combinations and parameter ranges that you consider to be part of the design space. That opens up basically around the seed design a parameterized set of design points. And obviously, you can walk through on that and do different kind of searches to figure out that what could be that design point which meets your requirements. The second is that on each level of a hierarchical design, you can swap in and out components and change configurations. Okay? So you can change the number of the wheels in the drivetrain. You can change from diesel engine drive to hybrid drive. So you can make significant structural variants for this. So indeed, the design space is built up such that the appropriate modeling language have these constructs and operators with which you can enrich, modify the overall design space, and represent, most importantly, the current state of the design space. Now, in this concept, the whole design process is basically narrowing down to certain points, regions in the design space by selecting configurations, trying configurations, and trying to find parameter combinations that meet the requirements. So that's ultimately the next step. Another important element here is the requirements. Requirements are coming from informal requirement documents, at least in this area. These requirement documents includes hundreds of requirements, in fact, in written form. What we do in Meta is that we formalize these requirements in the so-called test benching. The test benches are models. These models tell how to evaluate a particular design against a family of requirements, because single or more requirements can be evaluated by a single test bench. There is clearly an interface between the test benches and the designs themselves. What has to happen, of course, when you create a design, you link up the design to test benches through these interfaces, and then you run the test bench. the test bench get back to you scores. And the test bench get back to you parameter values. Right now in the tool chain, there are between 70 to 80 test benches. The test benches are built up and form a library that can be used by the designers. An interesting twist is that you can associate or compose with the test benches not only point designs, but design spaces also. So this whole thing may be a design space which might include different structural, configurational variants and parameter ranges. And when you do that composition, then the infrastructure, when you run the test bench, goes and evaluate the test bench for the whole design space. What you have a certain control over in what granularity you have to go through, or you want to go through on the design space. But ultimately, this is a totally automated process. And you get back after the test bench evaluation an occasionally gigantic amount of data. That data is used by another tool component, what I'm not talking about, which is basically a parametric optimization package, which can do multi-objective optimizations, finding Pareto optimals, provide excellent visualization for different suite of parameters, and basically you can use it for narrowing down into those kind of architectures and parametric combinations that meet the requirements or provide the required optimum what you would like to go after. Now, so altogether, this cyber-physical problem really creates a multi-domain challenge, right? If you look at the physics, there is a hierarchical decomposition from assemblies, sub-assemblies down to the components. The representation should be rich enough to provide support for the automated composition and also to provide opportunity to use on the different levels, particularly if you go up higher levels, simplified representations. For example, it's one of the techniques which is used to create the so-called surrogate models on higher levels. The surrogate models are basically multi-variable nonlinear regressions that you gain using some neural net techniques and so forth, such that you describe some kind of behavior in a compact way, so you don't have to rerun the whole analysis. There are physical domains, the usual thing, electrical, hydraulic, mechanical, thermal, electromagnetic, and of course there are different model abstractions. Model abstractions, I will not talk much about it, but that's a pretty important issue. Right now, the program uses, of course, the static abstractions, the static behaviors. The design space exploration start up with the rapid exploration based on static properties, trimming out all of those parts of the design space that obviously don't meet structurally or static parametrically the requirements. Then the process go on and start using more detailed model that now includes dynamics. One major part what we use is the lump parameter dynamics using the Modelica models, but we are actively pursuing two other variants. One is the so-called qualitative model abstraction. If you remember or you looked at it, that's Johan de Cleer's work on qualitative physics, qualitative modeling. And that group is part of the overall team, and they are pursuing contracting the design space using qualitative reasoning. That is under extensive test, so that's not integral part of the whole design space. We have another group from SRI, and the SRI folks are Ashish Trivedi. They are working on relational abstractions and they derive approximation, finite approximation for the dynamics, and do hybrid system analysis. Scalability in all of these cases is a major issue. So it's clearly there are no miracles. There's a lot of ongoing work is right now with that part of the program. Certainly, we understand how to derive and how to auto-generate the large simulations, and indeed, the program successfully met the first set of hurdles with the evaluations based on long-parameter dynamics. The cyber part is another interesting domain, obviously. It has also hierarchical decomposition, different behavioral abstraction layers that are usually differing in terms of timing, semantics, and refinements. I won't touch upon this. We published this several places. There is a tool chain which goes through on this and links basically the cyberspace to the physical design such that the workflow ultimately allows you to design or define first in terms of continuous dynamics, the controller behaviors, and then another part of the tool chain kicks in, which is doing it, the approximation. It's a computational approximation. Model integration languages. So as you see, in all of these design flows, you typically have these major phases. One is the conceptual design part, then the detailed design part when you already have dynamics, and then, the so-called preliminary design phase, and then finally the detailed design phase in which you use finite element, not so detailed software generation and so forth. But the bottom line here is that there are many, many tools involved here. It is absolutely impossible to build up a tool chain such that you redevelop everything. Accordingly, it would be totally futile to imagine that now we will develop a language for the whole design flow, a new language for the design flow. That doesn't make any sense. Therefore, what we do is that we try to understand how to structure that space and what we need to develop languages that are meta-specific but reuse everything which the tools dictate. So altogether, that problem specified for us two kinds of semantic challenge. One is to develop the vocabularies, what the whole meta and the whole program is using. About 1.5 years ago, we had a task force set up for several months that really did nothing else, just built up the vocabularies, find the standards for that. That included units, name of physical interactions, terms that are used in component models in the appropriate industry. And the computer science name for that is the so-called epistemic semantics. You can structure this into a formal ontologies, and ultimately you standardize for the program that this is the terminology what we use. Now, the other part is the modeling languages themselves. Modeling languages are, in that sense, orthogonal. They are using terms that are defined in the ontologies. They add more structure define formal semantics for the modeling language itself in terms of the structural semantics and behavioral semantics. And of course, everything is interlinked. So right now, what really the language specification in meta means that we have these vocabularies that are standardized and used in the program. They are not static, they are continuously evolving. And there are the modeling languages that are clearly meta-specific. Now let me talk about this meta-specific modeling language concept. Yeah, that just shows the overall information architecture in terms of the ontologies and the different modeling languages. Let me just save you from going through on all of these names. So when you need to answer that, what should I do in terms of modeling to glue together all of these things? Then obviously your primary question is that should I go with defining another modeling language which covers all of this space? Should I use, let's say, SysML as an integration language, or what? Now, whenever you want to give an answer to it, obviously, it's not a very academic question. Ultimately, what it depends on the tools and the availability of the tools. On one hand, you want to reuse tools. On the other hand, you really want to preserve some freedom in expressing abstractions as you like, particularly when you create such integrated design space. Ultimately, these pressures led us to develop the concept of these model integrated languages. So on one hand, you have the tools. These tools have their own rich modeling languages. What we do is that we capture only those concepts in these modeling languages that we need for linking together the models. So we tremendously narrow the semantics complexity toward the model integration. These are expressed here with these semantic interfaces, as we like to call them. These semantic interfaces abstract out some semantic element from the individual tools, and then we enrich those in a model integration language with concepts that you need for describing the interactions across. That defines a model integration language, what we call sci-fi. Because the number of the tools, methods, what we use is changing. Sci-fi is not a static language. It's changing. It's changing as the tool suite underneath is changing, as the requirements, the dominant pressures are changing in the program. So all of this is fine, but of course you pay a price for it. Because when you talk about a changing language, what you use for model integration, the standard which relates to it, or the specification which relates to it, cannot be based on the semantics, which is ultimately a gentleman agreement among the tool developers for it. So it has to be kept tracked precisely. And that brought in the need for developing another section of the whole tool chain, what we call the semantic backplane. And that semantic backplane provides a formal framework in which we represent the so-called structural semantics, behavioral semantics, and semantics for the model transformations, what we use in sci-fi, in the model integration language, and all of the tools that are related to composition and gluing together the models, filtering the models, sending models toward analysis tools, and so forth. That semantic backplane is built on the top of a language that came out from Microsoft Research. One of our previous students actually continued his work there. The tool name is Formula. I can really recommend that you take a look at that tool. If you type in Microsoft Research/Formula, then it's an open source tool. It's built on the top of Z3, and that's really an excellent formal framework to do these kind of things, what we use it for. So that's altogether the pursued direction in the language from the point of view. There is another part of the story here that has to be used as an argument. Why can we afford to change such an important part in the program, like the model integration language? That belongs to how we build up the tools that are our internal tools that we use for modeling, design space representation, and so forth. The usual tool infrastructure is that you have some kind of modeling language which is fixed in, like Simulink or others, or Modelica. and you have its own mathematical and physical foundation and semantics specified. Obviously, when you want to develop another one of these, then you always face the issue who will pay for the tools that relates to a new language, except if you use the metaprogramming and metaprogrammable tool infrastructure, and that's what we do. So we have this so-called model integrated computing infrastructure that is our traditional path, what we developed really in the last 20 years. It has a suite of metaprogrammable tools. You can model the semantics of the different modeling languages and automatically customize the tools toward different domain-specific modeling languages. So that's the key enabler with which we proceed, and that's what we use quite extensively. Now, I think that it's better if I hung up and just let me go to the final introduction. You can see the slides and so forth. Yes, so ultimately, where are we this? So codec by construction really is a very important goal. We believe that at least at this point, and particularly when you deal with physical systems, the most important thing what you have to do is to do deeper modeling and cross-domain modeling. There are techniques with which we can deepen it. Verification still remain a major challenge. There are many scalability problems what we struggle with, but certainly the progress is good. I believe that at the half of this program, we are over some of the major hurdles. So we now have sufficient evidence that the whole thing can be done, at least in the drivetrain context. To do it more in the finite element in these kind of domains, that will be another huge hurdle which comes in the next year. But at this point, we are positive that the whole thing can be done. So thank you very much for your attention.
Thank you very much. So, time for some questions. Yes, just a second. So you get
Thank you. Yeah, thanks for the talk. I have a question on this model integration language, and also you showed a slide with some interfaces before.
Yeah.
So I was wondering what is the connection between the two, because I didn't see those interfaces in the model integration language. And secondly, you said that the meta models are restricted for the task, because you have to restrict the semantics of what you expose from each tool towards sci-fi, right?
Right.
Isn't that dependent on the project? Because for different projects, the interactions are different. So your evolution of sci-fi should be based on the project itself.
No, I, of course, have other slides that show it better. Okay, so first of all, the interfaces. When we expose the interfaces, the interface specifications are captured through the meta model of these interfaces in sci-fi. So that's part of sci-fi. When I told that there is a semantic interface, the semantic interface is really nothing as how a modeling language shows up. What's the projection of the complex semantics of a modeling language from the point of view of the integration? Okay, so that's all. So let me show here one example which looks where the diagram looks complicated, but actually not so much. Here you see a suite of languages that we use in the long parameter dynamics modeling. It has modelic a hybrid Brown graph. SMOL is what we use in our software definition areas. True time, we use true time, and of course FMUs and FMU interfaces where you don't model internally, as you know what the FMUs. Now, what we show here, what are the obligations, what you have to do when you have these models, integrate them through sci-fi, and then you want to see some kind of behaviors in the integrated models. So there are many levels of integration. One level of integration is what certain tools requires, that you have to use denotational semantics, and you have to have the equations, right? So you can get that such that you have to have the equation-based representation of the models in the appropriate language. Obviously, you cannot use FMU if you want to do that. Plus, you describe the structure in sci-fi, the interactions in sci-fi. Then when you compose everything, you take these interaction specifications, translate it also in equations, symbolic equations, and you gain basically the total integrated block set plus the interaction representation symbolically, and you gain all of the equations that now describe the composed system, okay? Now, in that case, what kind of things we needed in sci-fi to do that part? The only thing which had to be expanded with it is that sci-fi does the composition through the interface in a particular way. It is usually simpler than it's, let's say, Modelica internally would allow, or Simulink would internally allow. But we stick with that to maintain some kind of compatibility across different languages. And when we generate the equations, the overall integrated equations, we take basically the sci-fi composition, connection concept and map them into the equation representations. There is a completely different integration techniques, what I would like to show here, and this is the so-called HLA level. HLA is a standard for distributed simulators. It's a US standard. It's over 10 years old. It's a much more sophisticated time management mechanism than what the CS do, what the FMU CS does. Now, we do, whenever there is a problem with large systems and simulation and time partitioning need, then you have to decompose basically the simulations into separate blocks that have the different timing requirements. HLA can allow you. So when we do the composition toward the HLA, what is the interaction level what HLA requires here? What is the semantics of those interactions, what you need? This is discrete event semantics. So the only thing what you need from that composition point of view is to get those concepts from the individual blocks that have discrete event semantics. And you don't care the rest. So that's basically the structure what we follow through in these different levels. And right now we have these 4 levels. So the equation-based, the FMES function and so forth, and the HLA-based. Yeah.
Okay, thank you very much. Any further questions or comments? Yep.
Thank you, Janos, for a very interesting talk and interesting initiative. So I think I have 2 questions, or maybe 3. Are you looking at a paradigm shift for actual users, for the actual developers? The disciplinary engineers will be using Simulink Modelica. Who is the stakeholder using sci-fi? And as was pointed out before, is sci-fi more of a framework because of the needs? It could be heavyweight, it could be lightweight, depending on the kind of harmonization you need across the languages.
So sci-fi, when we design sci-fi, then our primary design objective to get away with the simplest conceivable language what you need for describing the interactions across models. And that releases a whole lot of pressures from being comprehensive, universal, and modeling everything. So we believe that the conceptualization what follow in sci-fi is very much it's a very utilitarian approach. When you want to do these things and you understand that you need that your whole design philosophy is based on design space exploration, composition, linking in other tools, then it naturally leads to a set of problems to how to define architectures, design spaces, and so forth. And I guess if someone wants to use that type of automation, then sci-fi provides the vehicle to do that. Sci-fi will morph. It will continuously change. And again, as I told, that what we want is to keep it on the minimal complexity, but document it very precisely. What does that mean? We had some early experiments actually with uses. Last semester, we had a student competition, which was designing a small amphibious vehicle, which was that big about. And 3 undergraduate groups did that. One from MIT, one from Berkeley, and one from Vanderbilt. And they used the tool suite, well, as the tool suite looked half year ago, or last summer, end of summer. And frankly, it was a pretty manageable task. The students designed it, built it. We ran a competition for them, and one of the competition criteria was that we evaluated how much the measured performance of the vehicle running the missions on the sea and the sand corresponded to the models. That was part of the scoring. Our students, we have 40 interns, and these students are doing the model curation. So I believe that it's ultimately a doable task to convey that information and semantic richness to students. For the design competition where professional engineers used it, so the only thing at this point what I can tell that yes, we got a tremendous amount of comments about all sorts of things, what we are very thankful for, and refined the whole thing. But ultimately, the design competition quite nicely survived, and there are good designs that emerged through this. And the revision will continue.
Okay, so let me then ask the last question. So going from sci-fi downwards there, I noticed that you only had in the Modelica, you had an arrow pointing down. So I have a question if you have some thought about modeling here, because both physics-based modeling and data-based modeling seems to be an important component which is somehow required underneath. And I can imagine that in your drivetrain, you have fairly good physical models, but in other applications, cyber-physical application, it could be so that there is not existing models currently, or actually out of the design phase, you realize that you need these models. Have you any thought about how one could integrate that type of process into this framework?
Yes, so as you thought, even in the case of the drivetrain, modeling was a major issue. So it is a major issue. So for example, we got a clear evidence that understanding what's the difference between modeling for composition, such that you prepare the model such that it's composable for other models to get a more complicated model, is totally different than modeling a system such that it will work somehow. People need to get really convinced that it's worthwhile to do component modeling instead of just system modeling. There is not a good understanding also, or it's not trivial that when you do modeling and abstractions in physics, it's a very different story when you do it in computing. Physics behaves as physics does, and there's always some epistemic gap between the model, what you build, and how the physical world will behave. And when you see that epistemic gap and you want to prepare for it, uncertainty cannot be described statistically that you can average out the lack of your knowledge. So so modeling is really a major issue. What we hope can emerge here, that people ultimately through crowdsourcing will be aspired to build up these model libraries. These model libraries are becoming better and better. So don't forget, this whole thing is becoming open source now. And yeah, we totally recognize that we basically cannot bail out people from doing the physical modeling. Now when we go to hull modeling, which is all sorts of properties that are based on finite element models, these are the vibration, strength, and all of these things, then even the concept of component is non-trivial. So that's, yeah, you're right. So there's a lot of problems what we need to deal with or understand.
Okay, thank you very much. So let's thank the speaker again. Thank you.